Okay, we're beginning chapter 16, electrical energy and capacitance. I think by Tuesday we'll be doing experiments with capacitors. So let's share the PowerPoint, and here we go. And what we open up with is capacitors. There's all sorts of types of capacitors, and it looks like the one at the bottom is a capacitor that they've actually taken apart. You can see this winding, this kind of a foil that is wrapped around a piece of paper. The piece of paper is acting as a dielectric, and we'll learn about dielectrics later. But there's a variety of capacitors. Even that little, at the bottom, there's a little, looks like a white bar with these little dots on it. Those are uh, uh, capacitors that they put on circuit boards, very small circuit boards, like the type that go up into space. Those are tiny little capacitors. So we're going to be talking about electrical energy and capacitance. Now, if we have this parallel plate configuration, you did something similar in your lab where you put a positive on one side and a negative on the other side, and you were to plot the equipotential lines. Well, perpendicular to those equipotential lines is the electric field. So we see an electric field here. The electric field is going from left to right because it's positive on the left and negative on the right. So the electric field is directed left to right, and there is electric potential energy here. If we were to put a positive charge at point A, there is energy to push it to the right, to at least to position B, and it's the work is done to move that charge from A to B, and the change in potential energy is PE final minus PE initial equals minus work. Let's see, the work from A to B is equal to the force of X times delta X. Well, the force we learned from last chapter, the F is equal to Q e to the X. Now, e to the X, E sub X is the X component of the electric field. In this case, it's right in line with the electric field. So the work from A to B is equal to force times delta X equals Q EX times X final minus X initial. So the work is equal to the absolute value of the work is equal to the absolute value of the charge times the electric field times the distance that it travels. Well, we know that work is equal to force times distance. So we also see that the work equals Q EX delta X equals the change in kinetic energy as this thing moves from the positive to the negative plate. It will gain the potential energy will, the change in potential energy will equal to the change in kinetic energy. So the potential energy is to negative work AB equals minus QE X delta X, and the SI units for this is joules. Force times distance is joules. So Newton meters is joules. Okay, we can compare this to the gravitational case. Here we have, on the left, we have a positive test charge moves from A to B. The electric potential energy decreases. When an object with mass m moves from A to B, the gravitational potential energy decreases. You have to do work to lift it, to get its MGH, the potential energy, up. When you let it fall, it loses that potential energy. Here, when a positive test charge moves from A to B, the electric potential energy decreases. So we have the conservation of energy. We have the change in kinetic energy plus the change in potential energy electric equals the change in kinetic energy plus 0 minus QED, uh, and that equals 0 minus the change in kinetic energy equals QED. Now we compare that to the gravitational case. We have kinetic energy plus the gravitational potential energy equals the change in kinetic energy plus 0 minus mgd. You may remember it as mgh, the potential energy. Um, so that equals 0. Uh, so the change in kinetic energy equals mgd, so the potential energy that it had. So there's a comparison of gravitational and uh, the electric gravitational potential energy and electric potential energy. So let's look at this some more. When a positive test charge moves from A to B, the electric potential energy decreases. The work is equal to 1/2 mv squared. That's uh, the uh, kinetic energy. The proton is going to have some mass plus the QED, the D being the distance from A to B. So delta V equal, we're going to define a volt here. Delta V equals VB minus VA is equal to the change of the potential energy divided by Q, Q being expressed in Coulomb, so, and PE being expressed in joules. So this SI units of electric potential is joules per Coulomb or volt. So volt is joules per Coulomb. The change in potential energy divided by Q equals minus Q EX delta X over Q. So you see the Q's cancel and you have the EX delta X. Oops, went a little far. So change in voltage V sub X is equal to minus EX delta X. So we have both expressions, and 1 Newton per Coulomb equals 1 volt per meter. Okay, and I think that's the last for this section. We'll continue on with 16.2.